grounds of the Royal Hibernian Academy. The painting was commissioned by the faculty and staff of Trinity College, Dublin. The man having his portrait painted is Ernest Thomas Sinton Walton, Fellow Emeritus of Trinity College, and once the maker of a most important discovery. Ernest Walton studied at Trinity College, Dublin, and took a double degree in mathematics and experimental science. In 1927, he was awarded a scholarship that enabled him to go overseas to do research. He was accepted as a research student in physics at the famous Cavendish Laboratory in Cambridge University. This group of faculty and students at the Cavendish includes 4 men who had already won Nobel Prizes, plus 5 others who were to win them later. These include Ernest Walton himself and the man who was to be his collaborator, John Cockcroft. The director of the laboratory was the great Sir Ernest Rutherford, soon to become Lord Rutherford. He it was that first discovered and described the nuclear structure of atoms. Walton's first work at the Cavendish was to try to discover ways and means of producing fast atomic particles without having to use unmanageably high voltages.
Shortly after I went to Cambridge, Rutherford sent for me to discuss a possible line of research for me to undertake. And he asked me, had I any suggestion to make about a line of research. This actually was a very wise thing for him to do. He was a wise person, and he realized that if he could get a line of research for every student in which the student was interested, he was much more likely to get good work out of that student than if the student got some work to do in which he wasn't particularly interested. Well, when Rutherford put this question to me, I suggested to him a method of producing fast particles which would not necessitate the use of very high voltages. Now, the reason that I did this was because following on Rutherford's transmutation of nitrogen into oxygen in the year 1919, there was a lot of research work done using alpha particles to bombard various substances. And in all of these cases, including Rutherford's original experiments, what happened was that an alpha particle would go into the nucleus of an atom and a proton would come out. And there wasn't anything very new coming out of this. And the experiments were very difficult because you had very limited supplies of alpha particles, and you hadn't got other types of bombarding particles. And it was obvious that if you could produce artificially streams of fast particles, you could get vastly greater numbers of particles than you could get from any radioactive substances. You might be able to use other types of particles which would give you other types of results. And a lot of interesting things might easily follow. But at that time, it was believed that in order to produce artificially fast particles of the requisite energy, you would have to use some millions of volts, perhaps 3 or 4 or even 5 million volts. And such voltages could not be generated in ordinary laboratories. And even if you could produce those volts, you'd have to get apparatus that would stand up to that voltage in which you could actually accelerate up particles to high energies. Well, about this time, we had a visit from a Russian physicist. He was a theoretical physicist by the name of Gamov. And Gamov was working out implications of the then new wave theory, which had been introduced in the middle 1920s. And he, in particular, was able to explain the emission of alpha particles from radioactive substances, explain how they got through the potential barrier that we knew surrounded the nuclei of atoms. Now, Gamow's results showed, or rather explained, a lot about the emission of alpha particles from radioactive substances. Cockcroft attended the lecture which Gamow gave in Cambridge, and he saw that Gamow's theory could be applied in reverse in order to calculate the probability of getting a particle from outside a nucleus inside. And it showed that quite moderate numbers of particles could be got in, but the chance was quite small. This didn't really matter, because if you're producing the particles artificially, you could produce enormous numbers of such particles. Now, Cockcroft brought this to the attention of Rutherford, and it was decided that Cockcroft would stop working on what he was doing. He was working in the bench next to me in the Cavendish laboratory, and it was on the deposition of metallic vapors onto cooled surfaces. And it was decided that he would give up this work, that I would give up trying to get these trick methods to work, and we'd combine and build an apparatus using perhaps a few 100,000 volts, and accelerate up particles and see if we could get them into the nuclei of atoms.
Cockcroft and Gamow talked together about the theoretical possibility of getting particles into the nuclei of atoms using voltages that could relatively easily be handled in the laboratory. Cockcroft had taken a degree in mathematics at Cambridge, but he had originally been trained as an electrical engineer.
Well, of course, it was he, in a sense, initiated the thing by pointing out to Rutherford this question of getting particles inside nuclei. He was a very pleasant person to work with, but he had other jobs to do besides work in the laboratory. He was, for example, junior bursar in St. John's College, and this entailed looking after the property, and he had to try and find some old bricks to repair parts of St. John's College, and he used to travel the countryside to find these unformed buildings. He was also a secretary to Kapitsa, and this involved him in quite a bit of work in the magnetic laboratory, which was just adjacent to the main Cavendish laboratory. So a good deal of the constructional work fell to me, and I quite enjoyed this. I always enjoyed working with my hands. Well, the apparatus consisted of a lot of large tubes. Now, we needed to get a steady high voltage. You can get alternating voltages very simply by the use of transformers. With this apparatus, what we did was we used reasonably high voltage from a transformer, and were able to multiply it up by a special circuit, which required the use of rectifiers, that is, turning alternating current into a steady current, and alternating voltages into a steady voltage. These rectifiers we had to make ourselves. They were not on the market. The only ones on the market would stand up to much lower voltages than we were interested in. But eventually the apparatus consisted of 4 large glass cylinders, each of them 3 feet long, stacked one on top of the other. So you had a column 12 feet high, and this was pumped out by a high vacuum pump, special type, under the floor. All of these things took a lot of time because you had to do an awful lot of this constructional work yourself.
The apparatus had a proton source at the top. The protons were accelerated in a vacuum inside a column of glass tubes by strong electrical fields. At the bottom of the apparatus was the target the protons were aimed at. In the first instance, a piece of the light metal lithium. It hadn't been easy to find glass cylinders suitable for building the column, nor was it easy to seal them together so as to maintain a high vacuum inside. Walton and Cockcroft used a specially developed type of plasticine. The observation chamber was shielded with lead salvaged from old batteries. This was needed to protect the observer when the apparatus was switched on.
Well, this happened one day in April in 1932. Cockcroft was not in the room at the time. He was over doing some work for Kapitsa in the magnetic laboratory. So when I got up to a high voltage and put on the proton current, I thought I'd like to see if anything was happening. We had rigged up a screen, as we say, of some of this willemite, so that if there were any fast particles coming out of the apparatus, they would produce scintillations in this substance. So what I did was I left the control bench. The apparatus was giving voltages of something of the order of 600,000 or 700,000 volts, and I crawled across the room on my hands and knees in order to avoid the high voltages, and I went into a little hut that we had built under the apparatus where you were quite safe from these high voltages and also shielded from the X-rays that were being produced in the apparatus. And when I looked in through the microscope, I could see a whole lot of little stars sort of suddenly appearing and just as suddenly disappearing. Well, I knew that this was a sort of thing that happened when alpha particles struck this willemite mineral. So I tried a few simple experiments to make quite sure I wasn't imagining that I was seeing things. And then I got on to Cockcroft, who was over with Kapitsa at the time, and he came over and he got into this little hut and made the observations, and he was satisfied that there was a genuine effect there. So the next thing we did was we got on to Rutherford, and he came along very quickly. He was always very interested when people were getting results, not so interested when they were slogging along with their apparatus trying to make it work. We managed to get Rutherford into this little hut. He was a big man, and so it took some maneuvering to get him in to sit on the little low stool. And then he issued various instructions, like increase the accelerating voltage or increase the proton current and so on. And finally he told us to shut down the apparatus, and he got out of this little hut and sat down on a stool, as his custom was when he wanted to talk. He hadn't given us any inkling up to that point as to what he had seen, but what he said at that stage was, Well, those scintillations look mighty like alpha particle scintillations. Well, this was very encouraging to us, for here we had a foremost authority on alpha particles in the world confirming that these scintillations which we saw were actually alpha particle scintillations. And then he went on to say that he ought to know an alpha particle scintillation when he saw one, because he said he was in at the birth of the alpha particle and had been following them ever since. Indeed, afterwards I thought that he might also have added that he was in at the christening of the alpha particle, because it was he who gave them their name.
The next thing was to use cloud chamber photographs to confirm that the particles were indeed alpha particles. The length and character of the track left by a particle in a cloud chamber tell you what sort of a particle you're dealing with and what its energy is.
Well, it was very obvious. What was happening was that a proton was going into the nucleus of an atom. Now, a proton has a mass of 1 unit on the atomic scale. Some of the lithium atoms, in fact the majority of them, have a mass of 7 units. So when you add the 1 to the 7, you get 8 units. There's a lot of surplus energy available, and the atom that has been formed in this way immediately blows asunder, and the two alpha particles come out, each of them of mass 4, and they come out in opposite directions with the same velocity.
As soon as the results had been confirmed, the triumphant Rutherford took Walton and Cockcroft to a meeting of the Royal Society and announced what they had done. Cockcroft and Walton themselves had already written a letter to the scientific journal Nature, briefly describing their results. The letter appeared a few days later. The press made a fuss of the achievement, though it was by no means clear that all the reporters really understood what had been done. They were also not quite accurate about the nationalities of the experimenters. But the one paper that was sure of its nationalities was the Belfast Evening Telegraph. Ernest Walton had been a pupil at Methodist College.
The experiment was important for a number of reasons. Here you had got a new type of disintegration occurring, where a proton goes into a nucleus and an alpha particle comes out. Previously, you had the opposite of that, but also this really gave you particles which were far more abundant than the alpha particles from any available radioactive source. And you had everything under control. You could control the energies of your protons. And it also was important because it had verified the deductions from the new wave theory that had been introduced a few years previously, and that Gamow's calculations using the new wave mechanics were sound. It was also important, but in a lesser way, because it was the first time that Einstein's mass-energy relationship was verified directly. This was simply that if you destroyed an amount of matter m, you got an amount of energy out, which was given by mc squared, where m is the mass destroyed and c is the velocity of light. And this equation meant that if you destroy a very small amount of matter, you get quite a large amount of energy out. But it was important in another way, in that you had shown by these experiments that particles of energies of some hundreds of thousands of electron volts were capable of getting into the nuclei of atoms and producing nuclear transmutations. And it meant that people, particularly laboratories, say in the United States, could then go to some of the large foundations which had money for research and say to them, we know that if we get the money to build apparatus producing fast protons, that we will get results. Previous to that, you could make no such promise. So for all these reasons, the experiments produced useful results.
The usefulness of the results was recognized by the world at large when Walton and Cockcroft were awarded the 1951 Nobel Prize for Physics. The Nobel Prize is awarded for the most important discovery or invention in the field of physics in a particular year. Cockcroft and Walton's citation said they were awarded the prize for their pioneer work on the transmutation of atomic nuclei by artificially accelerated atomic particles. But by the year 1951, the atom bomb had been invented and used, and the hydrogen bomb was on the way. In the minds of many, the words splitting the atom are associated with nuclear reactors and bombs, but there is very little connection. Ernest Walton explains.
There were two discoveries essential for the atomic bomb. There was first of all the discovery of neutron by Chadwick, and then secondly there was the discovery just at the beginning of World War II of the fission of uranium, which is essential for the atomic bomb. Indirectly, it would have had some sort of influence because it led to the development of the big accelerating machines, particularly in the United States at the time, such as these big cyclotron type of apparatus. And these could be used for investigating the properties of uranium nuclei. And you're getting information, but the work was not directly involved with the bomb.
Can you tell me what is the kind of satisfaction that you get out of doing physics?
Well, the satisfaction is much the same as anybody gets out of discovering something new, whether it be the satisfaction that an explorer gets when he visits hitherto unknown territory, or the satisfaction that an inventor gets when he invents some machine that will do something that no machine before was ever capable of doing. So I don't think the pleasure you get out of it is essentially different from these pleasures that people experience in various spheres in life. It's certainly very, very pleasant to have some results that nobody has ever heard of before, results that may lead to important consequences and so on. In this case, it was particularly useful and nice because up to that time in the Cavendish, I'd been working there for quite a number of years without having any results to show. And in fact, when it came to writing up a thesis for a PhD there, I really had very little to show in the way of positive results. It was always descriptions of works, of experiments that failed. Apart from some theoretical calculations which I was able to do on the problems of keeping particles going round, say, in a circular ring. But Rutherford took a kindly view of the thesis and agreed to giving the degree.
In 1934, the man who Rutherford had kindly agreed should get his degree returned to Trinity College, Dublin, where he became Professor of Physics and head of the department. Today, his portrait is finished and will be hung with the portraits of all the great scholars of Trinity. Well over half a century after he made his discovery, Ernest Walton was still the only Irishman to have been awarded a Nobel Prize in a science.